Welcome to day 3 of the Snowflake Masterclass. Today we're diving deep into the heart of Snowflake's performance, the micro-partition architecture. Imagine your data not as one massive block but as thousands of tiny immutable columnar blocks, each called a micro-partition. Every time you load data, Snowflake automatically sorts and organizes it into these micro-partitions, each holding between 50 and 500 MB of uncompressed data. This columnar layout means only the columns you actually query are read from disk, slashing unnecessary I/O+. Micro-partitions are never modified. Updates or deletes simply create new versions, enabling powerful features like time travel. Metadata headers store min-max values and counts for every column, setting the stage for efficient query pruning. This design is what lets Snowflake handle billions of rows with ease. Now let's talk about how Snowflake turbocharges queries with pruning and clustering. Pruning is the secret sauce. Before any data is read, Snowflake checks your query filters against micro-partition metadata. If a partition's min-max values don't match your filter, it's skipped entirely, no wasted reads. This is why writing SARGable predicates like direct date ranges is crucial. Wrapping columns in functions like year forces a full scan and kills performance. For massive tables, clustering keys become essential. Natural clustering happens when data lands sorted, but for multi-terabyte tables with complex filters, explicit clustering keys help keep related data together. Snowflake manages reclustering in the background, but remember, high cardinality keys can trigger costly reclustering cycles. Always balance scan savings with maintenance costs. Let's move to query diagnostics and the dangers of disk spilling. Snowflake's Query Profile tool visualizes every step of your SQL execution, highlighting bottlenecks like table scan or join filter. If you see high operator expenses or full table scans, it's time to optimize your predicates or clustering. Disk spilling happens when a query needs more memory than available. Snowflake writes temporary data to SSDs, slowing performance. If even SSDs overflow, remote spilling to cloud storage occurs, causing major slowdowns. The fix? Scale your virtual warehouse up for more memory or optimize your joins and aggregations. Exploding joins where non-unique keys create massive row counts are a common culprit. Pre-aggregate with CTEs to keep joins efficient and memory usage predictable. Snowflake's caching layers are your best friends for saving credits and boosting speed. There are three: the result cache, which stores exact query results for 24 hours, the local disk cache, which keeps raw micro-partitions on SSDs, and the metadata cache, tracking stats and offsets. To maximize cache hits, make sure your queries are identical and avoid non-deterministic functions. Materialized views take this further by precomputing heavy aggregations, perfect for slow-changing tables and repeated queries. But beware, frequent source table updates can rack up maintenance costs. For pinpoint lookups, the search optimization service builds fast access structures, ideal for high cardinality columns like UUIDs or emails. Each optimization tool has its sweet spot. Choose wisely based on your workload. Finally, let's master scaling and concurrency. Vertical scaling, making your warehouse bigger, gives each query more memory and CPU, perfect for large, complex jobs. Horizontal scaling, adding more clusters, lets Snowflake handle many users at once, preventing query queues. Tune the max concurrency level for your workload. Raise it for lots of small, fast queries, lower it for heavy analytics. Use auto-suspend to avoid wasting credits on idle warehouses. Set it low for buy dashboards, higher for ETL pipelines. Monitor query queuing and resource usage in your logs, and always structure queries to minimize network data transfer. By following these best practices, you'll keep your Snowflake environment fast, efficient, and cost-effective.